Oh, can you hear me? Thank you. So, so I announced I announced about the final exam date and time on the Blackboard, and then as I mentioned, we will take the online exam for the final exam. So that means you need to take the final exam at your home. So, and then for this online exam, we will use the lockdown browser. So if you use this lockdown browser, then you cannot access any other internet except the Blackboard, I think so. So we will use the lockdown browser. Also, your desk and then the answer sheet should be monitored by your cell phone camera through the Zoom. So so we are using Zoom for the normal classes. So I believe everyone can use Zoom. Also, I believe everyone has everyone has a smartphone, and then if you have smartphone, then you can install the mobile version Zoom on your smartphone, and then you can turn on the camera on your smartphone to monitor the your task or you during the exam. So basically, we will use the lockdown browser and Zoom meeting tool for the online exam. Okay, so after today's class, I will post the quiz, but this quiz will be taken through the lockdown browser. So actually, people taking the final exam, you need to install the lockdown browser, and then I believe you can use the lockdown browser on the Windows operating system or Mac operating system. So Mac PC or Windows PC. So then the purpose of this quiz is to make you prepared for the this online final exam. So I will post the quiz after today's class. Also, I sent the survey for the time and date for final exam, but unfortunately, some students are not available for the some candidate for the this final exam date and then time slots. So actually, I will share the result. Here's the, okay. Oh, this is the survey result. So yeah, some students are not available for these time slots, but I have no idea why this class time is not available for some student. Why? I have no idea. So why this time slot is not available? Some final exam for other courses or so I have no idea. Yeah, so yeah, so I wrote that please check the boxes if you are not available. So So actually this, if you check, so you need to check the box if you are not available. So it's the some opposite of the normal survey. So if you are not available for this date and time, then we may take the final exam on Saturday or Tuesday, maybe December 22nd, because on Monday, the 21st, I'm not available, unfortunately. So yeah, so I will generate another survey form, and then also I will post this link for the another survey form on the Blackboard. Okay. Yeah. So you know, I know that this is not a good situation because the COVID-19 pandemic is getting severe. So yeah, it's not good. But please do your best until the end of the semester. Okay, and then I hope everyone keeps safe and healthy during this final exam period. Okay. Yeah. So we will have the last class on the Monday, next Monday. So, and then, so I hope I can complete the chapter 5 in today's class. Okay. So, do you have any questions about the final exam? So, any suggestion? Okay. Yeah. So, yeah. So I understand, but yeah. So actually, in the maybe previous semester, I also survey which day is available for student, but some student did not participate in the survey, and then after the final exam time is was fixed, and some students said, "Oh, I'm not available." That was the also problem. Yeah, it's not easy, okay, actually. Okay. I will generate another survey, and then also I post the survey on the Blackboard. Okay. 계절 수업? 그런가요? And then do we need to take the final exam at night? Maybe after 7 p.m. Is that possible? Okay. Okay. Yeah. So let's start today's class about the virtual memory. So in the previous class, we introduced about the concept of the virtual memory. So actually, some students are familiar with the terminology virtual because we frequently use the what's that? It's a hypervisor application actually, and then these hypervisor applications called the virtual platform. So actually the popular hypervisor application is the VirtualBox. One of the popular, this VirtualBox is the one of the popular hypervisor application. So with this VirtualBox, we can install the, actually we can make the virtual hardware, and then we can install the another operating system on this virtual hardware system actually. So actually in the computer engineering or computer science field, the virtual means is the fake or some illusions. So it's not real, but on the virtual environment, software or some other application runs like such like the application is really running on the real hardware, but this hardware is actually fake. It's not real. So you need to understand the terminology virtual. So that is also true for this virtual memory. So I mean that this virtual memory is not real. It's a fake memory, but the programs or application use this virtual memory like the real memory. So that's very interesting. So actually in the previous class, I took the example of the load instruction like load x1, 0, x2. So actually until now, we think like that. Oh, this address is the address space for main memory, and then that is also true, but this is the address for virtual memory space actually. So, and then also I explained why we use this virtual memory in our computer system. That the first purpose is to use the main memory, is the DRAM memory, like a cache of the secondary storage, like storage devices. Why? Actually, so why we use the cache? Because of performance. But the size of cache is smaller than the size of the main memory. That is also true for this memory, this concept. So actually programmer wants to use the infinite memory, but in our real world, the size of a memory is finite. That's why we use this space for this physical memory as the cache of some virtual memory. So that means this is the size of the real physical memory, but to the programmer, the computer system provides the very large memory. Then how can we store this large amount of data to this small physical memory? So we can use this small memory like a cache. That means if the data is used frequently, then we can store this data in the physical memory. But if the data is not used, then we can this data onto the storage device. So to the programmer or application, this is the virtual memory space, and then every data can be stored in any space of this virtual memory space. But in reality, this is the virtual memory space. In reality, some part of data is found on the DRAM, and then another part of data is found on the storage. So the first purpose of the virtual memory is to use this It's relatively small size of DRAM as cache of the large size of virtual memory space. So that is the first purpose. And then the second purpose of virtual memory is make operating system manage the some space of this main memory space dynamically. So it may be somewhat difficult to understand because until now we do not consider about the operating system, but this virtual memory is actually managed by operating system. So it is also some mixed region of the operating system and the computer hardware. But in our real operating system, like Windows or Linux or Mac operating system, we already know that in the operating system, many processes runs concurrently. So that means this process is the independent kind of applications. So many processes runs concurrently. So that means the memory space required by this process is allocated to the memory space of the computer system. That is the physical main memory space. So what's the problem? This is some memory space, but some part of the memory should be assigned to the program A, some part of the memory space should be assigned to program B. But when the program is compiled or written by programmers, we do not know how this memory is assigned to the multiple applications or multiple processes. So programmers actually do not know about this dynamic situation. So this memory allocation is managed by operating system dynamically, and then so actually this program accesses the virtual memory space, and then this virtual memory space is mapped to the real space, is the physical memory space based on the operating system mapping table. So this so this virtual memory concept is also used in order to manage some multi-process environment managed by operating system. Okay. So let's see how this virtual memory is mapped to this physical memory. So this is the example like x1, x0, x2. So this is the address of the load instruction, but I said this address is actually virtual address, And then because this address is virtual address, this virtual address should be translated into the physical address. Because this is the fake. So it's not real world. But in order to access the data, this data should be stored in the real physical memory. Right. Even though the application used this virtual address space, the data should be accessed from this physical memory. So this data has the address. This address should be translated into the physical address. It's a real location of data in the physical memory. Okay. So, and this should be translated. So, for example, no, this virtual address is the 0x00A, and then in the physical address, this should be 0x11 like F like this. Actually, A. So the address should be translated. So, and then for this translation, we use the mapping table. This mapping table has the information of the virtual address translation into the physical address like this. So this is the virtual address, and then this example shows that the virtual address has the 48 bits, and then this is the physical address, and the physical address has the 40 bits. So I have a question. This is a question. So physical address space has the 40 bits. Then what is the size of this physical memory? Size 2 to 40. Okay. That is 2 to 10 is kilo, 2 to 20 mega, 2 to 30 is what? 39 is too large. Is giga, and 2 to 40 is tera. It's very large memory. It's a 1 terabyte of memory, right? 그렇죠? 킬로, 메가, 기가, 테라. So why this is kilo? Because 2 to 10 is 1024, and then is really similar to the 10 to 3. So that's why in binary 2 to 10 is kilo. Okay. Kilo, mega, giga, tera. So this physical address has the 40 bits. So that means this 40 bits of address is mapped to the 1 terabyte of physical memory. But how about this virtual memory? Virtual memory has the 48 bits. Then what is the size of this virtual memory space? 2 to 48 is like 2 to 8, 40, so 256 terabyte. So that means for the programmer, the virtual address space is seen to the programmer. So programmers can use this amount of memory space, but this large memory space is mapped to the smaller physical memory space, like this 1 terabyte. So, but you need to remember that this is the fake. So this is the fake world. So real data should be stored in this physical memory. That's why this virtual, in order to access the data in the real memory, real computer system, this virtual memory should be translated into the physical memory. Okay. So, for this translation, we use the mapping information from this virtual page number to the physical page number. Also, so this RSV part. So in this example, this LSP part has the 12 bits. It's the 4 kilobyte. This LSP part is not translated into the physical address. So what does that mean? So actually, this lower part of the virtual address called the page offset is directly copied to the page offset of the physical address. So what does that mean? So virtual, in order to translate this virtual address to the physical address, this translation is performed by 4 kilobyte chunk. Okay, so that means, for example, this 4 kilobyte. It's a 12, like 1, 2, 3, 4, 5, 6. So this is the virtual address. Then this virtual address is, if this virtual address is translated into the physical address, then this page offset part is not translated. It is used as, it's the same value as the, for the physical address. This page offset part has the same address, like 456. So, but this upper part is the virtual page number part is translated into the physical page number, like F1, like this. So this translation is performed for the 4 kilobyte of chunk, and then this chunk is called the page. It's called the page. So that means one page is the basic unit that is translated into the virtual page number into the physical page number. Okay. And then this is also this figure shows the this figure shows the concept of the virtual memory. So as you can see, the virtual address space is larger than this physical address space. So that means some part of the virtual address space cannot be translated into the physical memory space. It's also true. So in this example, the size of the physical memory is 1 terabyte, but the size of the virtual memory space is 256 terabyte. So if we compare the size is very different. So what does that mean? Some parts of the virtual address space cannot be found in the physical memory space. Then this part of the data is stored in the disk or storage device. Why? The size of the storage device is much larger than the size of the main memory. So we already know. So this part is stored in the some part of the disk address. So if in the Windows operating system or Linux operating system, so you can find this dedicated space on the storage device. So in the Windows operating system, you can find the page region. So this page region is some dedicated space for this temporary space for this what's that? This virtual address space stored in the disk or hard disk drive or a solid state drive. And then on the Linux operating system has the swap space and then the swap space is used for this data. The data that is not stored in the physical memory, but this part is stored in the swap space of the disk. So if the data is found on the storage device, then it will be very slow to access this data. So, and then I will explain how this case is handled by operating system and computer hardware. Okay. So you need to remember that this virtual address should be translated into physical address, and then for this translation, only some upper part of the virtual address is only translated into the physical page number, the physical upper part of the physical address. But this page offset part is not translated. So think like that. If the every address space is translated into physical memory space, then this translation information will take lots of space. So, and then that is inefficient. So that's why we use this page offset for this virtual address to physical address translation. And then what is the page fault? So actually this case. So this is the virtual address, and then actually the operating system managed this mapping table, like a virtual page number to physical page number mapping information, and this information is stored in the page table, and then this page table is actually stored in the main memory, like it's a DRAM. So when this virtual address is requested, then operating system access this page table, and then when this page table has some information about the translation information, such as the virtual page number to the physical page number, or if this virtual page number cannot be mapped to the physical page number because this page is not found on the main memory, then this page should be found on the disk or storage device. And then this case is called the page fault. So what is page fault? This is the virtual page, and then but this page does not exist on the main memory, like DRAM, and then this page exists on the storage. That is the page fault. So on page fault, this page must be fetched from the disk. What's the problem? It will take very long time. It is because the storage device is very slow compared to the main memory. So if the requested page is found on the disk, then this page should be first read from the disk, and then this page should be transferred to the main memory. But reading this page from the disk will take very long time. So, and then this event is called the page fault. And then this page fault is a kind of exception because it will take a very long time. Okay. So I said this virtual address to physical address translation is the some mixed part of hardware and operating system, because the hardware also need to support this process like TLB. It will be explained later. Also, some data movement should be supported by hardware, but like this page fault event should be handled by operating system. And I said that this is a kind of exception. Then what was an exception? I explained is the rare event in hardware. So why this is an exception? This is rare. So you may think that it's not rare because actually this page fault frequently happens in our computer system, but in the viewpoint of this computer processor is very fast. This page fault event is relatively rare. So that's why this page fault is handled by operating system as a software. So, and then the operation of this page fault is also is programmed in the operating system. So if the page fault happens, then exception occurs in the processor, and then what will happen? The exception handler is called by processor. So operating system change the program counter to the exception address of the exception handler, and then this page fault is handled. Okay. OS. And then I said that this translation information is managed in the page table. So this page table is actually a structure that maps the virtual page number to the physical page number. So that's just a structure. It's a software structure, not hardware. So actually it's very simple. So this is the virtual page number, and then here is the mapped physical page number. Also, this structure has some control bits like valid or dirty, like cache. So this is the basic structure of the one page table entry, I call the PTE. So when the virtual page is requested, then VPN virtual page number is given to this page table, and then this virtual page number is scanned in the page table, and then this mapped physical page number is computed from the virtual page number. So this is just a mapping table, like 0.001 to 0.FFF, like this. Also, this page table has some information about the if the page table something like if page table exists on the main memory or on the disk space, or also if the target page is modified, that means it's dirty, so it modified or not. Also, this page table has the information about some like if this page entry is valid or not. So like reference 3. So let's see how the virtual page number is translating the physical page number through the page table. So let's start from the load instruction, like load x1, 0, x2. So I said that this is the address. So actually this address is the virtual address. So this is the address, like virtual address. And then, so actually this lower part of the virtual address is not translated because it's the page offset. So normally the size of the page is the 4 kilobyte. It's a fixed size. So the lower 12 bits are not translated. But these upper bits should be translated. So when the process, so the process is the actually is the application. No. Some application has multiple processes. So if the process is launched on the processor CPU, then this page table register is assigned to each process. Okay. So this page table register indicates the location of the page table. It's the page table. Then where is this page table? In the main memory. So do not be confused. This is the software structure and then managed by operating system. So this is the DRAM. And then some software structure called the page table is stored in some part of the DRAM. Okay. So this page table register indicates the address of page table. Okay. It says the page table is the software structure managed by operating system. Okay. So this page table register indicates the location of the page table, and then the virtual page number is the part of this address, virtual address. So this virtual page number is scanned on this page table, and then if this virtual page number is found and then valid, and then this the entry of the physical page table has the physical page number information mapped to this virtual page number. Okay. So this physical page number is read from this page table, and then this PPN is translated into the PPN, physical page number, and then this is becomes the physical address. So with this physical address, the DRAM, the data on the DRAM is accessed. Do you understand what I am saying? Okay. 좀 이해가 되나요? Okay. Okay, good. So this translation is the translation from fake world to the real world. So, and then, but data exists in the real world, and then in order to access the data in the real world, this fake address of the fake world should be translated into the address of the real world. And so, okay, so this real world address is the physical address, and then the fake world address is the virtual address. So in the application runs on this fake world actually. And then also I explain about this figure. So this is the page table, and then this page table has some control bit like a valid or dirty or reference bit. Also the page table entry has the physical page number information mapped to the virtual page number. So, and then as you can see, if this page entry is invalid, like 0, then this page exists on storage devices. Okay. And then this case is called the page fault. So, and then I said that this virtual memory concept is very similar to the cache concept of the cache memory. So as you can see, some part of page exists on real physical memory, but some part of page exists on this disk storage. So this is then we learned that in the cache memory, the size of cache memory is smaller. So that means some data cache block is evicted from the cache if the cache capacity is not enough. Cache has enough available space. So that is also true for this page table, because page table manage the virtual address space. So sometimes some page should be evicted from the physical memory because the physical memory has enough space for the new page fetched from the disk. So in this case, the old page should be evicted from the main memory. So for this case, we need the replacement policy like cache memory, but the most popular replacement policy is the LRU. So least recently used LRU, and then this policy is also preferable for page table. Okay, but you know, the size of the main memory is very large compared to our cache memory. So this page table cannot be managed like the LRU of the cache. So this technique is used. So this is the reference bit. So reference bit means that this page is accessed recently. So if the page is accessed, this reference bit becomes the 1. But this reference bits on the page table is periodically cleared by operating system, and then this reference bit is 0, then this page is not accessed recently. So this page can be evicted from the page table. So you may think that, oh, this is not it's not a real LRU, because sometimes this reference bit is periodically cleared by operating system. So sometimes, even though the page is recently accessed, but unfortunately, after some time, the operating system delete this reference bit on the certain page. That is also possible, but this is some preferable manageable method to handle the LRU in the page table. Okay. Also, this page, this is also cache. So you need to set the write policy. So what's the write policy of the cache? So write through and write back. But for this page table, we cannot apply the write through, because if this page is updated on the physical memory, and then this page is updated, modified, and then with the write through policy, this modified page should be returned to the disk just after the page is modified. What's the problem? Disk is very, very slow. So we cannot use the write through policy for this page. So we use the write back policy. So how can we apply the write back policy? We can set the 30 bit. So 30 bit means that this page is modified in the memory. And then this page is evicted from the memory, like DRAM. Then if the 30 bit is set as 1, then this page is returned to the disk. Okay, so if not, this page is just ignored. Okay, so then let's learn about the TLB. So TLB is the translation look aside buffer, TLB. So I said that this page table exists on main memory. Main memory is DRAM. What's the problem? Main memory is very slow. So, but think like this: load instruction is executed, but this load instruction uses the virtual address, and then in order to access the data on the main memory, so data, this virtual address should be translated into the physical address. But in order to get this physical address, we need to access the page table, because we don't know about this physical address of the data. So actually, when the load instruction is executed, and then if the data exists on the main memory, not cache, then what happened? First, this page table is accessed, and then the corresponding page physical address is got from page table, and then using this page address, the main memory DRAM is accessed. What's the problem? In order to get the physical address, we need to access DRAM once more for the page table. What's the problem? DRAM is very slow. So in order to access the page table, you need to access the DRAM. So actually, in order to access the data on the DRAM, you need to access DRAM twice. Once for page table, then once for the data on the DRAM. And then that's very inefficient because DRAM is very slow. What's the solution? If the memory is slow, we can use the cache. So this TLB is the cache of TLB is the cache of page table. Do you understand? So what is the cache? If the data is accessed and the data is requested, then this data is stored in the cache memory. Then what is the data of the page table? The data of the page table is the virtual page number to physical page number mapping information. So that is the data of page table. So this information, like page table entry, is cached in the TLB. So TLB is the cache of the page table. So this TLB size is actually very small, like typically 16 to 512 page table entries. But the good thing is that so the page size is the 4 kilobyte. So accessing the page table has very strong locality. So if we have the TLB, it's a cache of the page table inside of the processor, then the hit rate for this TLB is very high. Okay. So this is the typical performance value of the TLB, like 0.5 to 1 cycle for hit, and then 10 to 100 cycle for miss. Miss rate is very low. Okay. So this is the concept of the TLB. So this is the virtual page number of the virtual address. And then, so like, let's start from the load. This is the address. So this, the virtual address is generated from the load instruction. This virtual address is sent to the TLB, translation look aside buffer. And then this TLB has the virtual page number. So virtual page number is used as the tag of the TLB. And then the physical page number is stored as the data of the TLB. So if this virtual page number is found on the TLB, then we can get the physical page number. So as this TLB is the cache of the page table, TLB has also these control bits like valid, dummy, and reference bit. Okay. So if this mapping information is found on the TLB, then we can get physical page number very quickly. And then using this physical page number, we can access the DRAM. Okay. But if not found on the TLB, then we need to access the page table, and then the remaining process is the same to what I explained before. Okay. So this TLB is just a cache of the page table. So as TLB exists, also we can define the operation of the hit or miss of the TLB. Also, this hit and miss of the page table is also I explained about the hit and miss event on this page table also. If the miss is the page fault. So and then I already explained. So and then for the TLB miss case, so that means this mapping information is not found in the TLB. In this case, so we need to access the page table in the main memory, and then if this information is updated to the TLB because it's cache, okay? So that is the TLB miss. So it's a TLB miss. And if page is in memory, and this is the operation behavior of the TLB miss. And then if the page is not found in the main memory, then this is the page fault. So it's a virtual address. Virtual address first access the TLB, is a cache of page table, and then we can think hit and miss case of TLB, and then if for the miss case, the page table in main memory is accessed. Also, we can think about the hit and miss. When miss is the page fault, then we need to access the disk storage. So that is how the data is accessed by load instruction. But this TLB miss is managed by hardware because TLB is the hardware component. So also this I said that TLB is the cache of the page table and it's managed by hardware. So that's why the TLB is fast. Okay. I also explain about the page fault case. Then, but we missed something. We missed cache. Like, so load x1, zero, x2. So actually, this is the address. And then I said that with this address, the cache should be accessed. So in this process, you cannot find the cache. I only mentioned the main memory. I only mentioned that this page, the requested page, exists on memory or disk. But where is the cache? So what's the problem? Problem is that there are two kinds of address for data. With the virtual address and physical address. So and then in order to access the data in the physical address, we need to use the in order to access the data in physical memory, DRAM, we need to use the physical address. But program use the virtual address like load x1, 0, x2, use the virtual address. Then how about the cache? So actually the cache is the kind of memory hierarchy. And then in real, actually, in order to access Actually, cache is used for better performance that for accessing main memory. So actually, in order to access the cache, we need to use the physical address, because this physical address is the real address that indicates the location of the data in main memory. So it's real. But problem is that why do we use cache for better performance? And then actually for the level on cache, what is important? Access latency is important. In other words, heat time is important. But what's the problem? If the level on cache is accessed by physical address, then so actually the load generate the virtual address, and then in order to access with the physical address, at least we need to use the TLB, and that is the translation. Even though the TLB is very fast, it will take 1 clock. That means if the TLB is accessed before level on cache, then the heat time will increase. And then it will also increase the AMAT, average memory access time. And then it will also increase the CPI. The performance is degraded. That's the problem. So in the processor, normally the level on cache is accessed by virtual address. And then level to cache is accessed by physical address. So you may think, oh, why address is different? But it is, but in actually we need to use the physical address for the cache also, because it's a real, it indicates the real location of the data. But because of the performance issue, the level on cache is accessed by virtual address. And then there can be some issues about this virtual address and physical address access issues, but these issues will be covered by advanced computer architecture course, not here. Okay. Okay. This is some operating system issue, like memory protection. So I said that the virtual memory is also used for managing multiple processes share the physical memory spaces. So that means by this page table, some space of the data, like a shared library, can be shared by different process, like different application actually. And that is also true. It can be shared, and then it frequently found on our real computer system. What's the problem? If this shared library is corrupted by this process, then this corrupted data may influence the operation of this another process, another application. That's the problem. So this memory protection is also applied to this page table, and then this is managed by operating system. Okay. So virtual memory is done for the undergraduate computer architecture, this course actually. And then actually this virtual memory has also many issues. Then you will learn about this virtual memory on the operating system course. Okay, good. And then this slide shows the summary of the cache and the memory hierarchy. So it will be helpful if you read the remaining slides. Okay, like so these slides explain about the memory hierarchy, placement, write policy, misses. Oh, so I need to explain about the source of misses. So this is called the 3C of cache, because this source of misses have the all C's. So this source of misses explain why miss happens on cache. So there are three different kinds of misses, like compulsory miss is called the cold miss. So it's also called the cold miss, and then capacity miss and conflict miss. So this compulsory miss means that, so initially the cache does not have any data. So if the data is firstly requested by program, this data should be fetched to the cache, but the first request is miss. So this is the compulsory miss, and it's also called the cold miss, because initially the cache is cold. There is no data. And then capacity miss. So what is the capacity miss? The cache size is small, then the data should be evicted from the cache. So the all requested data cannot be stored in the cache memory. So that means the data should be evicted, but this, even though then, and if this evicted data is requested again, but this data is not found on the cache. So this miss caused by limited space, limited capacity of cache. So, and then this type of miss is called the capacity miss. So for this capacity miss, we assume that the cache is the fully associative cache. This is because we need to distinguish it with the conflict miss, like this. Then what is the conflict miss? So we know that the fully associative cache has the best performance for the same size of the cache, right? Because with this fully associative cache, we can store any new data on the any available space of the cache. But the set associative cache or direct mapped cache, the index has the limited number of cache blocks. And then with this limited number of cache blocks, even though the cache has the empty space, if the set is already full, then this one of cache blocks to be evicted from the cache. And then this eviction may cause the additional miss. And then this type of miss is called the conflict miss. So these are the 3C of the cache, and then this 3C explains the source of misses, the cause of misses. Okay. So this is the not fully associative cache. So this is the cache design trade-off. So if we increase the cache size, we can reduce the capacity misses, and that is obvious, right? But what's the problem? Access time can increase. Increase associativity, we can reduce the conflict miss. right? But what's the problem? Access time also cost increases. If we increase block size, then we can reduce the compulsory misses. But cache is polluted. So this 3C of the cache can be used for explaining the cause of misses. Also, it can be used for explaining how the cache performance and cost or cache performance can be configured. Okay. Okay, I need to stop here. Cache coherence is another advanced issues. So this is the end of the chapter 5, the memory system of the processor. And so actually this course, the 3 important concepts is the ISA, pipelining, and then memory hierarchy. So try to remember these 3 important things in computer processor. So that is important. That those are important in the undergraduate computer architecture course. Okay. Okay. Do you have any questions? Okay. Thank you for listening, and let's see next Monday. So it's the last class of the course. Okay. Thank you.